I'm gonna start a new chapter 19, because technically, I think we are slightly behind the tentative schedule. So I will not waste any time. So we're gonna directly start a new chapter, carboxylic acid. So this chapter will be very short because carboxylic acids we already seen many times already, actually, from the general structure. So the carboxylic acids are those class of compounds has this COOH group. So basically you see a carbonyl group, but one side connect to the OH group. And this group, this COH group, we call it carboxyl group. Okay. So the nomenclature of carboxylic acids, I will not be spending time in the classroom. My past experience proves that you guys can learn well enough by reading by yourself, because it's a set of rules. Okay. But I could test briefly, but not a lot. Okay. Now we directly jump to the structure and the bonding. And actually, the structural bonding of carboxylic acid we already discussed in chapter 16. I hope you recall when I was explaining that the why the reduction of carboxylic acid requires lithium alumina hydride. Nothing else works. Okay? Only lithium alumina hydride can reduce carboxylic acid, because the carbonyl group in carboxylic acid has unusually high stability, which can be illustrated by these 3 resonance forms. Okay, so here is the 3 resonance forms you can write for formic acid. Okay, so as you can see that you could write 3 resonance form indicate that this carboxylic acid has a pi electron delocalized over a system of 3 atoms, means OCO. The pi electrons are fully delocalized over 3 atoms. Okay, so this, let's say, compare with relevant compound we have seen earlier. Say like this one. Okay, acetaldehyde, this guy. Okay, if you look at this guy, you only can write 2 resonance forms. So yes, you can write this one. These 2 resonance forms, but you cannot write a 3rd resonance form. Okay, and this already had. This basically suggests that in a carboxyl group, the positive charge, the pi electrons delocalize over a wider range than the carbonyl group in aldehydes or ketones. Okay, so or you can say that the OH group, okay, OH group is a better electron donating group than the LQ group when it comes to stabilize a positively charged carbon. You see, OH group is a better electron donating group, so it can better stabilize a positively charged carbon here. Okay, and we already have seen this a number of times already in quite a few chapters. In chapter 13, we have seen that OH group is a more powerful activated group than the LQ group, right? Because OH group can donate the lone pair. Since here OH group can donate the lone pair, so the carbonyl group much better than LQ group does. So that makes the carbonyl group in carboxylic acid has a substantially, the higher electron density than the carbonyl carbon in ketone aldehyde. So the consequence is the carbonyl group in a carboxylic acid is substantially less electrophilic than the carbonyl group in ketone aldehyde. So that's why ketone aldehyde it can reduce with sodium boron hydride, okay, or catalytic hydrogenation. But the carboxylic acid, because the carbonyl is less electrophilic, it requires more active reducing agent, lithium aluminum hydride. And this electron delocalization also has other consequences. Okay? So when you look at the most the electrophilic atom in the carboxylic acid, okay. Actually, the most electrophilic atom is actually acidic hydrogen in the carboxyl group. So because of this carbonyl carbon still is electrophilic, okay, but because it's the positive charge gets delocalized to oxygen so efficiently, so it enhances the acidity of this particular proton, so that this proton is more electrophilic than this carbonyl carbon. This is something worth noting. Okay? Then if you look at this resonance form, these three resonance forms, which atom is the most nucleophilic? Nucleophilic atom. Which atom? OH group? See, how do you spot most nucleophilic atom from resonance form? The nucleophilic atom. Nucleophilic atom, you should be seeking for atom has a highest concentration of negative charge. It's carbonyl oxygen because that's the one you're going to see greatest amount of share of negative charge. So the most nucleophilic atom is a carbonyl oxygen, and the most electric atom is hydroxy proton. Carbonyl carbon still electrophilic, yes. Still electrophilic because of it from the central resonance, still electrophilic, but sizably less electrophilic than the ketone aldehyde, the carbonyl carbon. So that's this structural property analysis can tell you. Okay? Without some kind of reaction, just look at resonance form. You see, oh, most electrophilic atom is actually the hydroxy proton. Okay. And this one it will be less electrophilic than carbonyl carbon, the ketone aldehyde carbonyl carbon. Still electrophilic will be less. Okay, and the most nucleophilic one is carbonyl oxygen. Okay, any questions? Now the physical property is that again, just like whenever we get physical property, usually we concern the boiling point the most, and the boiling point is exclusively depends on intermolecular interaction among the same type of molecules. And here, if you look at a group of compounds, 4 of them, they have a similar molecular weight. You will see that understandably, the hydrocarbon has a lowest boiling point because the only major intermolecular interaction is kind of induced dipole-induced dipole interaction. Okay? So it has the weakest intermolecular interaction, understandably. And this guy has a permanent dipole-dipole interaction. It participated among those molecules. So yes, my boiling point is sizably higher. Okay? And the alcohol, usually we consider out of typical compounds with similar molecular weight, alcohol is the one has the highest boiling point because alcohol, they can have hydrogen bonding involved. Okay, but now this time we see the carboxylic acid, okay, has even higher boiling point than alcohol, even higher. Okay, so why? We know alcohol, they can have pretty strong hydrogen bonding involved. Okay, so only explanation you can have to explain the carboxylic acid could have even higher boiling point than alcohol because carboxylic acid can have even stronger intermolecular interaction than alcohol. And we know hydrogen bonding is the strongest intermolecular interaction we can have among neutral molecules. Okay? Ions are different. Okay? For neutral molecules, hydrogen bonding is the strongest intermolecular interaction we can have. So carboxylic acid, they are neutral, so they still have a hydrogen bonding, but their hydrogen bonding sometimes is even stronger than the alcohols. Why is it stronger? Is because if you have a carboxylic acid, they can have two molecules, two copies of them. They have the carboxyl group forming a hydrogen bonded dimers. Okay, and by doing this, they can enhance the ability of hydrogen bonding of each other. So basically, they make this interaction, okay, more closer to covalent interaction. Okay, they have a synergetic effect. So one hydrogen bond enhances the other hydrogen bond. Okay, so become the cooperative hydrogen bond. Okay, so this hydrogen bond is so strong that even, let's say, you heat this propionic acid to its vapor state, even in gaseous state, most molecules remain as hydrogen bonded dimers. So even in gaseous state, in vapor, most of propionic acid, they still remain as dimers. So what's net effect? The molecular weight effect is doubled because of this. So that's why the boiling point is so much higher. Carboxylic acid, usually they are reasonable water solubility because they can form hydrogen bond with water. Okay. Now, this is for physical property. Okay. So the only physical property you need to understand that because of the, I would suggest you draw this hydrogen bond dimer, you're going to have a better appreciation of what's different about hydrogen bonding situation in carboxylic acid compared to hydrogen bonding in alcohol. In alcohol, the hydrogen bonds are relatively random, okay? But the hydrogen bonding in carboxylic acid, they are most of them, they are in the form of dimers. Okay? And this dimer formation, they actually enhance each other. At least 4 or 5 times, you have a better appreciation of this. Okay? It's not that difficult. It takes 10 minutes at most. Okay? Then the next thing we're going to discuss is about a very unique property of carboxylic acid, implied by its name, carboxylic acid. So carboxylic acids, why they have this name? Because they are generally the most acidic organic compound you typically deal with. I'm not saying they are the most acidic organic compound you can work with, but they are the most acidic organic compound you typically work with. So although they are still weak acids because of their, if you judge that by pKa values, they are typically between 2 and 6. It's sizably small, less acidic than hydronium ion. Hydronium ion, usually it's the acid, the reference acid. If any acid is stronger than hydronium ion, we call them strong acid. If any acid weaker than hydronium ion, we consider weak acid. That's just a general way of classification of acids. And the hydronium ion has a pKa about minus 1.5. So obviously, all those carboxylic acids are still weaker than the hydronium ion. So they are still weak acids. So why the carboxylic acids are so much more acidic than alcohols? That's probably the class of organic compounds has a structure closest to the carboxylic acid. Okay, so the why carboxylic acid is so much the more acidic than alcohols, it can be best explained if we look at their ionization equilibrium. Okay, we actually look at this in chapter 1, organic 1, but it doesn't hurt to look at it again. So if you look at the ionization equilibria of alcohols under the carboxylic acid, you will see this is alcohol ionization equilibrium. This is a carboxylic acid equilibrium. So if you look at the conjugate base of alcohols is alkoxide, and the conjugate base of the carboxylic acid is called carboxylate. And this conjugate base, in this conjugate base, the negative charge is much better delocalized than the negative charge in this conjugate base, because in this negative charge, the conjugate base is fully local. In this conjugate base, the negative charge is completely localized on oxygen. No other way to escape, to spread. Okay? But in this conjugate base, the negative charge is well delocalized, by which can be the best represented by two equally stable resonance forms. See, these two forms, they are resonance forms, they are equally stable. So that means negative charge is actually completely equally delocalized over two oxygen atoms. So that dramatically enhances stability of the conjugate base. So that makes if the conjugate base is more stable, means less basic. Okay, and it's several, like 10 orders of magnitude less basic than this one. Okay, so that makes the conjugate acid 10 orders of magnitude more acidic. Okay? So that's the major explanation why the carboxylic acid is so much the more acidic than the alcohol. The carboxylic acid is so much more acidic than the alcohols. Okay. And if make the carboxylic acid solution pH to 7, then the major species in the solution will be carboxylate. Okay, so in the physiological conditions, usually for humans, pH is about 7.4. Okay, something around that. Okay. You say 5, okay, but 7.4, but close to the neutral value. So most of the carboxylic acid in your bloodstream, they mostly exist in carboxylate form. So common one is the lactic acid. Okay, if you, especially after your exercise, your body is gonna have you probably can feel your muscle, what called, I don't know. Yeah, sore, right? Muscle. That's because of the lactic acid. Okay? And mostly they exist in the form lactate, the conjugated base of lactic acid. Okay? And then that's about just vanilla carboxylic acid. The pKa is usually around 5. Okay? But if you modify the structure of carboxylic acid, you will see it's the acidity may change as a result. So for instance, if you're using a chlorine, it's a famous electron withdrawing group, replace one hydrogen on acetic acid, and then this this compound, okay, this called chloroacetic acid, will be sizably more acidic than acetic acid itself, because of chlorine is a pretty powerful electron withdrawing group, so it can enhance acidity by inductive effect. And when it comes to inductive effect, always a few rules apply. Distance matters, the electron withdrawing group, the electron withdrawing power of the group matters, and the number of electron withdrawing groups matters. So here we are showing the distance from the electron withdrawing group to the carboxyl group matters. If the shorter distance it is, the stronger the acidity enhancing effect is going to be. Okay? So like this one is 2.8, very large acidity enhancing effect. And one more carbon away, the effect is sizably weaker. And another carbon away, the effect is even weaker. Okay. And then the electron withdrawing power of the substitution also matters. You see the fluorinated version, okay, is more acidic than chlorinated version, okay, and the chlorinated version should be more acidic than brominated version. But just somehow there are differences, probably not large enough to be seen. But still, if you really can look at pKa values, give one more digit, you probably can see chlorinated version is more acidic than the brominated version. Then if you have additional chlorine, here is 1 chlorine 2.9, additional chlorine, even more acidic because the effect accumulated. Okay? If 3 chlorines, even greater. Okay, see this 1 chlorine 2.9, 2 chlorine 1.3, 3 chlorine 0.9. So the effect accumulated. Okay, so basically just the same as we have learned earlier. Okay, I'm gonna just stop here. Maybe we're gonna discuss next class. Next Monday exam. Okay, as usual, same rules apply. And if you care about the answer keys, we'll upload somewhere around the 4 p.m., 5 p.m. somewhere.
Can I look at the test again?
Yeah, sure.
Super fast if I go to class.